Okay, we're back. So let's see where we are. Okay, here's the schedule. After today, there'll be 4 more classes. The 17th and 19th next week, 24th and 26th the week after that. Then that Thursday, I guess it would be the 27th, is reading day, not that it matters to you in this class. And then exam week starts. And so what I want to do is this. I'm going to make what's listed on the website now, homework 6, I'm going to call that the final exam. But that's going to be a take-home exam. So it's going to be different than the other homeworks in the sense that the other homeworks you were allowed to consult with other people, ask any questions you wanted, because the main objective was teaching rather than grading. But for the final exam, I'm going to count that heavily toward the grade. So it's a take-home exam. So even though it just says 20 points on it, you should look at it as an exam in which you're on your honor not to discuss it with anybody else, not to give any answers or to receive any answers. You can ask any questions in class. You can ask any questions of me. I can decide whether or not to answer those questions. Now, it'll be due on May 5th, which is the end of the semester, the last official day of the semester. That's a Friday. And let's say less than or equal to that date. So the earlier you hand it in, the better. However, it may be that you feel that you can't do it in the time allotted because, well, who knows. So what I want to do is allow people to get an I. So if you want an I, you should tell me as soon as possible by email and give me a schedule. And the way this works is I can give an I if there's work that remains to be done and I'm specific about it. So if you ask for an I would say that the reason is that the project has not yet been completed or something like that. And then on this form that I fill out, I have to give a date by which that I will automatically turn over to some other grade, which I will give you, ordinarily a C. So in other words, if you don't hand in your final project, your exam, by whatever the due date is that we agree upon, then the grade automatically reverts to what you would get if in fact you didn't hand in the final exam. Then what you're supposed to do is I fill out this form, you sign it, and so what you should do is think of a reasonable time that you require in order to do the exam, 2 weeks, something of that sort. And then put that date down, and then that'll be the due date for you for that exam. Now, if you feel that you can't take an incomplete because you're graduating or some reason like that, then that's okay. Doesn't matter. It's your choice whether you take it or not. The best thing for me, of course, is if you simply get everything in on time, which means that you would get everything in at least by May 5th, the end of the semester. Okay, so send me an email if you want to get an incomplete in this and do it as soon as possible, although that doesn't mean immediately. You don't have to do it until you see what the exam is and how much time you have and where you stand on all this. No. What is currently listed as homework 6 is the exam. The difference is that you can't consult with other people on how to do it, and you can't tell anybody else how to do it either. So you're taking it as if it were an exam. Now it says it's worth 20 points. That's what it would be worth if it were homework, but actually it'll be worth more than that in the sense that it's the exam and all the other points were for homeworks. So the homeworks were designed for the purpose of teaching rather than grading specifically. Although, of course, if everybody got grades on those things and those grades accumulate. So if you didn't do them, your grade isn't going to be too good, and if you did, then fine. But basically, this is like, up to this point, the points are all homework, and then these 20 points is to say a 20-point exam. But the 20 points, the fact that it's 20 points doesn't mean anything since I'm going to count it more heavily than the other homeworks. Now that also means that you should do more than the minimum, because in some sense it's easy. There's a right answer. Get the right answer, then you get 20 points. But I really like to see more than that. So when it says show all your work, explain things. Be as neat and as complete as possible. And if you want to do more, that's fine. For example, although it doesn't ask you to do this, the question is to take homework 5 and answer the same question except for constant service times instead of exponential service times. Now, the simulation is exactly the same, so everything is based on the theory. This is theory for MG1, so it should work for any distribution of service times. Constant is just a specific one. Actually, it's the easiest one to use as a specialization of the general case. However, you could also take exactly the same algorithm and do it for exponential service times. And in that case, that would give you a check because you've already done the exponential service times case in homework number 5. The difference was in homework number 5, you used a method, rate up equals rate down, that works only for the exponential case. But if you've done homework 5 and you did the theory, then you know exactly what the answers are for the case of exponential service times. So when you do homework 6, if you run your algorithm for exponential service times, then you should get exactly the same results that you got in homework 5. And then, of course, when you run it for constant service times, you should get different answers because the service time distribution function affects the answers. Okay? So I'll give you more information on that because right now you don't know how to do that. I haven't told you the theory behind it, so that's what we're going to get into. Yeah? Well, I'm not sure. I can't give you an exact weighting. What I have is I have two things. I have the sum of all your scores for your homeworks, and if you did them, then you should have gotten close to the max because if most people did. So if you did them, you got the points. So that's kind of a cushion. And then I look at the final exam, which, as I say, I'm asking you to do maybe more than it asks. It's up to you. It depends on how nicely it's done, not only whether you get exactly the right answer. And the best, of course, if you've done your homeworks and you do very well on the final exam, then you get an A. And if you do a little bit less, then it's an A minus and a B plus and so on. So it's sort of my judgment. There aren't that many people, and I have some idea as to what you all know because there's a small enough number so that I actually can correlate. I understand exactly each person's homeworks with the person. So I take it all into account and use my best judgment. So the answer is, I don't know. There is no specific formal weighting. Anything else? Let's see. I've back some more homeworks here. Gohal and Lou. Homeworks. So the question as to how difficult homework 6 is really depends on how much I tell you. If I don't tell you anything, then presumably you could get it from the book, but that's probably difficult. If I tell you a lot, there's nothing to it, so I have to figure out as I go along how much information to give you and how much you're supposed to figure out on your own. Okay, any questions about that? It's better to take an incomplete, take an extra couple of days or a week, and do a really good job than to do a rush job and get it in on time. So now I want to start talking about MG1 in detail. And last time I gave some stuff that leads up to that, including the Policek-Kinchin formula, which gives a formula for the expected value of the waiting time in the MG1Q. But now I want to derive more. I want to get the generating function of the number of customers that are found by an arrival or left behind by a departure or seen by an outside observer. Those are all the same thing in the MG1Q. And get the Laplace-Dieltjes transform of the distribution function of waiting times in the case of which service is FIFO. And that's also called the Palachuk-Khinchin formula. And the expected value of the waiting time can be obtained from that by differentiating and setting the argument equal to 1 or 0. Okay, so the embedded Markov chain, here we go. This starts on page 210. Embedded Markov chain. Embedded Markov chain. Now, there's a whole theory of Markov chains, and I want to use a terminology so that it communicates with other things you might know or might see, but I'm actually not going to use any formal theory from Markov chains. Embedded means that, well, it means this. The way we're going to look at it is to say that here's time, and I'm going to look at the instance at which service completions occur. So let's say the server is available, and a customer arrives, and he makes the server busy for a certain length of time, and then he leaves. And then another customer arrives, and then his service time occurs later, and then he leaves. And another customer arrives, and there's his service time, and he leaves, and so forth. And the strategy here is to relate the probabilities that describe the number of customers left behind by a departure in terms of the number of customers left behind by the previous departure. Now, that will turn out to be what's called a Markov chain because it's sufficient to know what happens at those particular points and what happens in between them. So I won't go into a big definition here. It's not important except to say that what we're doing here is we are taking this Markov chain and we're embedding it in the continuum of time. And but that doesn't matter. I'm just using the terminology. Now, what I want to do is I want to derive equation 812. And 812 is for the generating function, which I'll call g of z, of the equilibrium distribution of the number of customers left behind by a departure. So I'm going to define this as being pi j star z to the j summed over all j from 0 to infinity. So this is the generating function of these probabilities. And pi j star represents the probability that a departing customer, that's what the star stands for, departing customer leaves behind j customers when he leaves, j other customers in the system, when the system is in equilibrium. And we're going to, once we derive that, then we can get all the information we want from that. So the first thing to do is to derive a formula for g of z, and according to 812, this is what the formula is. It's z minus 1 eta of z divided by z minus eta, excuse me, not eta of z, eta of lambda minus lambda z, divided by z minus eta of lambda minus lambda z times 1 minus rho. And in this formula, the z is just a dummy variable. It's that z right there. The lambda is the arrival rate of the Poisson process. And the eta, the rho, is the utilization of the server. And the eta is a Laplace-Dieltjes transform of the distribution function of service times. So different service time distributions have different transforms, and the transform appears right here in the generating function. Okay, yes, question. What was that?
Is lambda the same interarrival time?
I still didn't get you.
Is lambda the same interarrival time variable we've been using this entire time?
Yeah, except it's not the inter-arrival time, it's the arrival rate.
Right.
Okay, so we're talking about MG1. So we have Poisson input, whose rate is lambda. We have general service times. We have one server, and we have the block customers waiting in a queue. So in the case of exponential service times, then this thing should reduce to the generating function for the distribution that you already know. That'll be a check. Okay, so what's eta? Eta of s. That's the Laplace-Dirichlet transform. So it's the integral from 0 to infinity of e to the minus st dh of t. And the notation I'm using here, probably not good notation, but that's what was originally used in the book. H of t is the distribution function of service times. So I probably should have called it f sub w of t. F sub x of t, distribution function for service times. And the H stands for holding time, which is the old teletraffic terminology. Okay, so you give me the distribution function of service times. I plug in here, I get eta, and that then gives me the generating function of the number of customers left behind by a departure. Yes?
Again, just a little question. I noticed that lambda is the only thing dealing with the arrival rate. Is this insensitive to distribution of arrival times?
No. Okay, the question is this result insensitive to the arrival process? And the answer is no. It works only for a Poisson process. So MG1, we're assuming Poisson input. We're assuming one server, block customers wait in the queue as long as necessary. We don't say at the moment what the order of service is, although later, when I get the distribution function of waiting times, I'm going to assume that the service order, the queue discipline, is FIFO. And the G, that's the big deal here. The G means that this analysis is going to work for any distribution function of service times. And I specify that through the Laplace-Dirichlet transform of the service time distribution function. Now, these guys represent the equilibrium probabilities of the number of customers left behind by a departing customer. And the reason we want to do that, as you'll see shortly, is that if I look at the system at those instants, that is separating successive departures, I know that successive departures are separated by a complete service time. And so therefore I can write equations that represent the number this guy leaves behind in terms of the number that this guy leaves behind and the number that arrive between their departures. And since I know that the length of time between their departures is exactly a service time, and I know they arrive according to a Poisson process, that allows me to write these equations and solve the problem. Now, if I took the viewpoint of the arriving customer, which at first glance seems more natural, then you could see that an arrival typically arrives during somebody's service time, which means that if I take that viewpoint, that introduces memory into the system, because that means that the state of the system at this time and what's going to follow is going to depend on the length of the interval that was interrupted, or it'll depend on the remaining time in the interval, whichever way I want to look at it, or it'll depend on the past time of the interval. Now, if those service times are exponential, that means that the interrupted interval has a forward recurrence time. That's the same as an ordinary service time because there's no memory. And it has a backward recurrence time that is the same as an ordinary service time. So that means that if I have exponential service times, the memoryless property of the exponential means that that taking the viewpoint of arrivals doesn't affect, doesn't bring any memory into the system. Doesn't affect the let me say this again. If the service times are exponential, then taking the viewpoint of the arrivals means that there is no memory in terms of the service time that's been interrupted, so that the remaining service time or the service time up to that point is the same as a full service time, and that makes everything simple. But if the service times are not exponential, that means that if I take the viewpoint of an arrival, I have to take into account the fact that the distribution of the service time that I've interrupted, that is the forward recurrence time or the backward recurrence time, depends, that is the forward amount, depends on how much time has elapsed since the start of the service time. That introduces memory. That makes things much more complicated. So to get around that, I look at the system at the service completion epochs, because then I know that from that point on, the only thing that's going to affect the future evolution of the system is the number of customers that's present at that time, and not anything having to do with how much time has elapsed in an interrupted service time. The difficulty is, or the trick is, that it doesn't at first glance appear that looking at the thing from the point of view of departures is sufficient to understand what's going on, because I'm really interested in the point of view of the arrivals. However, we have a theorem that says in an equilibrium, in a system that changes only one step at a time, that the departure process and the arrival process are to see the same thing. So that means that what we'll find out, what we'll use later, although we don't need it now, is that the probability, write it here, the probability in equilibrium that an arriving customer finds a system in state J, that's the same thing as the probability that in equilibrium a departing customer leaves a system in state J. So this is because it's a one-step process. I talked about this theorem last time. And pi j is equal to pj. The arriving customer sees what the outside observer sees because we have Poisson input, pasta. So what we're going to do is we're going to solve for these guys and then interpret these guys as these guys, which are therefore equal to these guys. However, in homework number 6, when the number of waiting positions is finite, it's not true that the departing distribution and the arriving distribution are the same, and so that's the major difficulty there. And the reason they're not the same, you can see it immediately, is suppose that I have n waiting positions. Well, the probability that an arrival occurs when all the waiting positions are occupied, obviously that can happen, and that's in fact the probability that you're interested in, because that probability represents the loss probability. That's the probability that an arriving customer finds all the waiting positions occupied is the probability that he's denied service because there are no waiting positions available. On the other hand, it's impossible for a departing customer to leave the system full. He can find the system full, but he can't leave it full, because if just before he departs the system is full, then just after he departs there has to be one idle position. So therefore, the probability in the case of MG1N, so this is what happens in homework 6, the probability that an arriving customer finds the system in state n plus 1, that's what we're interested in, and that's generally greater than 0. But the probability that a departing customer leaves the system in state n plus 1, that equals 0 because that never happens. So therefore, the theorem does not apply in this case, as I'll explain why when we get to homework 6. And so that means that I have to do something to the analysis where n is infinity, where I don't have this problem, in order to handle the case of a finite buffer size. Okay, so what we want to do now is we want to write equations that are going to allow us to calculate the generating function, which it'll turn out as that, and then we're going to use the generating function to get the information we need. Okay, so the idea is given by equation 813. And what it says is this. This is just the theorem of total probability. The probability that customer number k plus 1 leaves behind him when he departs j other customers is equal to the probability that customer k plus 1 leaves behind j, given that the previous customer, customer number k, left behind I times the probability that the previous departure, k, left behind I, summed over all I. Okay, theorem of total probability. Now, this is always true. The question is whether or not I can figure out what these transition probabilities are, these conditional probabilities. Yes?
What's that last probability?
This is the probability that the number of departures left behind by the kth departure, that is, the number of other customers left behind by the kth departure, is equal to I. So the probability that a departure leaves behind j is the probability that the previous departure left behind I times the conditional probability that the departure leaves behind j if the previous customer left behind I, summed over all possible values of I. So this is just a theorem of total probability. It's always true. But by embedding our process at the service completion epochs, I'm able to calculate these conditional probabilities. Because if the kth guy left the system in state left behind I, and the kth plus first left behind j, the difference between that value and that value depends on the number that arrived during the time that separates them. And that time that separates them is exactly a full service time. And so that allows us to solve the problem. Yes?
Does that mean that in the diagram that we have drawn, we say that the last one, anything on the diagram, yes?
In this diagram,
Yeah, the last arrow.
okay, suppose this is,
Yeah, let's say that was a departure.
let's say we're looking over here.
Yeah.
Okay,
So
so
does it mean that all the customers before that departure are j, and the customers previous to that departure, that is,
what it means is, okay, and I'll clarify this when I write out this equation. This is a departure. This is customer k plus 1 departing, and this is the previous customer, k departing. Now, we're going to say that we want to calculate the probability that when he departs, just after his departure, he leaves behind j. And we have the probability that the previous departure, just after his departure, left behind I. So if this guy leaves behind j and this guy leaves behind I, then what must have happened is that a certain number, enough to go from I to j, will have arrived during that interval. And since that's a complete service time, we know what those probabilities are, and that will allow us to solve the equations. Okay, so what I have to do is I have to write down what these conditional probabilities are. Then I have to make an argument about taking the limit as k goes to infinity, but that's nothing, although technically it's difficult, and then solve the problem. Okay, so let me write down what these conditional probabilities or so-called transition probabilities are. So this equal sign, that's theorem of total probability. And has nothing to do with queuing theory or embedded chain or anything. It's just that that's the way I choose to look at it. I choose to look at it at the departure points. Okay, now the question is, does that get me anywhere? Okay, so here are the transition probabilities. What's the probability that customer number k plus 1 leaves behind j, given that the previous customer, customer number k, left behind I, where I happens to be 0? Okay, I is 0. That means that the previous departure left the system empty. Okay, now if he left the system empty, what that means is that the kth plus first departure, when he arrived, he must have found the system empty, and therefore the only way he can leave behind j is if during his service time exactly j new customers arrive. Okay, here's the diagram. In this case, here is customer number K, and he leaves the system empty. So that means that the customer who was the next customer to leave must arrive when the system is empty. And then when he leaves, that's customer number K plus 1, the number that he leaves behind him will be the number that arrived during that service time. Okay, so what's that probability? That probability, that's equal to, well, let's see, I give myself some more space here. That's equal to the integral from 0 to infinity of. Now, this is, here is the probability that the service time, right here, is exactly t. In the book I called it zeta, I think. This makes things look more confusing. Okay, so I'm going to call it t. So this is the probability that this service time lasts exactly t, and if this guy left behind 0, this guy finds 0, so he will leave behind j if during t exactly j arrive. And since they arrive according to a Poisson process, that probability is lambda t to the j over j factorial e to the minus lambda t. So that's the transition probability for the case in which I is equal to 0. That's the first term. Okay, now let's take the case in which I is greater than 0 and j is greater than or equal to I minus 1. Okay, so what that means is that if I is greater than 0, then we're back over here. The picture looks like this. Okay, so let me draw the picture here. Here is customer K, and he leaves behind I. And here is customer K plus 1, and he leaves behind J. Now, j must be at least, if I is greater than 0, that means that when this customer left, as soon as he leaves, there are still other customers in the system. So that means that the number that must arrive in order that I go from j to I, or excuse me, from I to j, is going to be exactly j minus I minus 1. So the number of arrivals here during this interval must be j minus I minus 1. If that happens, because remember that when this customer leaves, he leaves behind one less than what this customer left behind because he himself is leaving. And then there are other customers that are arriving according to a Poisson process. So for example, if customer number K leaves behind 10 customers, then customer K plus 1 can't leave behind less than 9. Okay? If I leave and I leave behind 10 customers, then if nobody were to arrive in this intervening service time, I would leave behind 9 customers. So therefore, the number that I'm going to leave behind has got to be at least one more than what this guy left behind. All right, let me write this down and then I'll go over this again. I think it'll be easier to see once I put it in here. So under this condition, I have the probability that the number of customers left behind by customer K plus 1 is equal to J, given that the previous customer, the kth customer, left behind I in the case in which I is not 0. So that means that the previous customer, when he left, immediately a new customer entered service because he didn't leave the system empty. So that means that the two departures are separated by exactly a single service time. And during that time, we know that one has left because when this guy leaves, he was one of the ones that was counted over here. Question? I minus 1. Okay, let me write down what this probability is. By the same argument, it's going to be the integral from 0 to infinity. The time separating those 2 points is a service time, so dh of t is the probability that that time is exactly t. And during that time, the number of arrivals must be exactly j minus I minus 1. Or another way to write it is j minus I plus 1. Okay, so one possibility is that the previous customer left the system empty. If he left the system empty, then there's a time from his departure until when the next arrival occurs. That next arrival will find the system empty. And then when he leaves, the number that he leaves behind are all those that arrived during the service time. But if I is greater than 0, that means that the previous customer did not leave the system empty. So that means that immediately a customer enters service, and when that customer departs, he will be the kth plus first departure. And so the number that he will leave behind will be the number that the previous guy left behind minus 1 plus the number that arrived during the time that separates them. Okay, so that means that the probability that I go from I to j in that intervening service time is the probability that during the service time, the number of Poisson arrivals is exactly j minus I plus 1, or j minus quantity I minus 1. Okay, finally, what's the probability, corresponding probability, that if I is greater than 0, and j is not greater than or equal to I minus 1, which means that j would be less than I minus 1. Well, that's impossible. That is, if this guy leaves behind 10, then the next guy that departs cannot leave behind less than 9. So if I is greater than 0 and j is less than I minus 1, the probability of that occurrence is 0. So then the conditional probability is the probability that the kth plus first departure leaves behind j, given that the kth departure left behind I, in that case it'll be 0. Okay, so now we have the transition probabilities for the different 3 possible cases. Yes?
Just to make sure I'm getting this right, you've got the probability that number of the n sub k plus 1 star equals I, given that n sub k star equals 0. Wouldn't that technically be wouldn't that be j given that n k star equals I when I equals 0? To make it consistent with the other two?
I think it's consistent. First of all, I have 3 cases. Okay. One case is where I is equal to 0. Then there are 2 cases where I is not equal to 0. And I'm talking about going from I to j. So if I is not equal to 0, then there are 2 possibilities. One is that j is at least I minus 1, and the other is that j is less than I minus 1. Now, if j is less than I minus 1, that's impossible. So therefore, the probability for that transition is 0. So if j is greater than or equal to I minus 1, then what is the transition probability? It's the probability that during this service time, right here, that the number of new arrivals is equal to this number minus this number plus 1. Because remember that when this guy leaves, one of the people he left behind was the guy who was now leaving. So I have to add in that 1. On the other hand, if the previous departure left behind 0, then this guy finds 0, which means that the number that he leaves is exactly the number that arrived during his service time. So the probability that if the previous guy left behind 0, the next departure will leave behind j is the probability that during that guy's service time, exactly j arrived. Okay, so I have the so-called transition probabilities for every possible case. So now I have to put them in here and simplify somewhat. So to simplify, what I'm going to do is I will now define the following. I'm going to define little pj that's the probability that in an interval that corresponds to a service time, whose distribution function is a service time, exactly j customers arrive. Lambda t to the j over j factorial e to the minus lambda t integral 0 to infinity. And by the way, this looks very complicated, but it's going to turn out not to be complicated because we don't have to calculate these things. When we take generating functions and transforms, everything is going to collapse and simplify. Okay, so I'm defining this thing here, and this is equation 817. So this is defined now for j equals 0, 1, 2, and so forth. And this is equation 817 in the textbook. So I'm defining little pj is the probability that during an arbitrary service time, I have exactly j arrivals according to a Poisson process. And now with that definition, I can take these conditional probabilities, these transition probabilities, and write them as follows. The probability that customer k plus 1 leaves behind j, given that customer number k, departure number k, leaves behind I, is equal to this. If j is equal to 0, it's exactly equal to little pj. If j is, if I is equal to 0, I equals 0. Okay, that's this case right over here. That one. If I is greater than 0, this one, and j is greater than or equal to I minus 1, then the answer is p sub j minus I plus 1. So this is the case where I is greater than 0 and j is greater than or equal to I minus 1. And if I is greater than 0 and j is less than I minus 1, then this probability is 0. Okay, so the probability that the kth customer, that the kth plus first customer leaves behind j, if the kth customer left behind I, is given by pj if I is equal to 0, pj minus I plus 1 if I is greater than 0 and j is greater than or equal to I minus 1, and 0 if I is greater than 0 and j is less than I minus 1. So we wrote this down over there on that board, and this little p, this corresponds to the probability that during a service time I have exactly j new arrivals according to a Poisson process. And this is the probability that during a service time I have exactly j minus I plus 1 new arrivals during a Poisson process, according to a Poisson process. Okay, so those are my so-called transition probabilities. Now, one thing to observe is that these probabilities do not depend on k. So they depend only on I and j. In fact, they don't even depend on I and j, but they depend only in the difference between I and j. Okay, now I'm going to plug these guys right here with this definition into these equations. So that takes care of these guys right here. And then I'm going to take a limit as k goes to infinity. So here's the key step, a key step. I'm going to say this. Suppose I take those equations 813 and I take the limit as k goes to infinity of the probability that the number of customers I leave behind, or the number of customers left behind by the kth departure, is exactly j. Now, if you remember, when we looked at the birth and death process, what we did is we wrote equations that had pj of t, the probability that the system was in state j at time t. And then we took the limit as t goes to infinity, and we argued intuitively, without actually proving anything, because this was way beyond the scope of the course, that under certain conditions that limit exists. And intuitively, it certainly should exist. It should be the distribution of the number of customers in the system after a sufficient length of time has elapsed so that the effect of the initial conditions has worn off. So we accepted that as being reasonable, that there was a limiting distribution, at least in certain cases. It turned out that that certain case was when the what corresponded to the utilization being less than 1. Okay, now I'm going to do the same thing here, except that instead of letting time go to infinity, I'm going to let number of customers go to infinity. So now I'm looking at the system in the limit so that I'm looking at the probability that a departing customer in equilibrium leaves behind j. And I claim that intuitively it's the same thing. It doesn't matter whether I talk about time going to infinity or I talk about number of customers going to infinity, because in an infinite length of time, an infinite number of customers will arrive, and conversely. So I'm going to take this limit, and I'm going to say that that limit then is independent. Of course, doesn't depend on k, and doesn't depend on the initial conditions, and it should be equal to pi j star. Now, this is, from a mathematical point of view, this is a big deal, because what I have to show is that in something called the Markov chain, that a limiting distribution exists. But in this context, it's kind of obvious that there ought to be a limiting distribution. So what I'm going to do is I'm going to take limits throughout this equation here, and I'm going to replace just as I did earlier, except previously, when I took limits, I was letting t go to infinity, and then I was replacing the probability as a function of t by the alleged equilibrium distribution at time t in infinity. Now I'm going to do the same thing here, except that instead of letting time go to infinity, I'm letting number of customers go to infinity. So I'm going to get rid of the dependence on k here. I'm going to call this a pi j star. And this is going to be pi I star. And this, as we've just seen, the transition probabilities do not depend on k. So therefore, when I take the limit, those guys aren't going to change. So the result is that I'm going to get this equation. And by the way, this is equation 819 in the book. And so what I'm going to get is this. I'm going to take limits, and and now I can interpret this directly. I can say the probability that a departing customer in equilibrium leaves behind j other customers is equal to the probability that in equilibrium the departing customer leaves the system empty. That's going to be the first term when I is equal to 0. And if he leaves the system empty, the probability that the next customer will have left behind j is the probability that during that departure service time, exactly j customers arrived according to a Poisson process. This guy right here. Plus, now I want to look at the terms between 1 and j plus 1. And then the terms after that are all 0. Okay, so then I'm going to have the sum as I runs from 1 to j plus 1 of the probability that the previous departure left the system in state I, and during that intervening service time, the number of new arrivals according to a Poisson process was exactly j minus I plus 1. This is true now for all values of j, 0, 1, 2, and so forth. And this is equation 820 in the book. Okay, so what did we do? We started off with the theorem of total probability, which expresses the number left behind by the kth plus first departure in terms of the number left behind by the previous departure and the probability that corresponds to jumping, going from state I to state J in that interval. And because we are calculating these probabilities at times that are separated by service times, that means that we can figure out exactly what these transition probabilities are. So here they are. The probability that the kth plus first departure leaves behind J if the previous departure left behind I is equal to the probability that exactly J arrived during the last service time if I is 0, exactly J minus I plus 1 arrived during the last service time if I is greater than 0 and J is greater than I minus 1, and 0 otherwise. Yes?
And so in that context, little piece of J would equal the lambda and the T would be one service time, correct?
The little piece of J, right here, these guys, this represents the probability that during a service time, the number of arrivals according to a Poisson process is exactly whatever that subscript is. Well, there it is. This is the probability that during a service time, the number of arrivals according to a Poisson process is exactly J. And I define that to be little piece of J. Okay? This is the probability that the service time lasts exactly T. This is the probability that during an interval of length T, if the arrivals occur according to a Poisson process, we have exactly J of them. And this thing sums it over all possible values of T. So this, again, is just a theorem of total probability. Then we recognize that what we really want to do is we don't want to look at these things for the kth plus first departure and the kth departure. We want to look at them for arbitrary departures. So we're just going to look at the probabilities from the point of view of two successive departures after an infinite number of departures have occurred. That is, as T goes to infinity. And we claim that there should be an equilibrium distribution. Now, to prove that there is such, and the conditions under which that's true, that's a big deal from the theory of Markov chains. But we don't have to do that here because it's sort of obvious that that must be true. In fact, what we can do is we can take it as being tentatively true. So we're going to assume that this limit exists and then see what we get. And then, in fact, what will happen is, out of that analysis will be the conditions for existence. So we're doing it kind of backwards. So I remember that at one time, early in my career, after my book first came out, a mathematician who was very distinguished guy in probability and queuing theory and stochastic processes complained to me that I was dumbing the subject down by making it accessible to people who didn't understand the theory of Markov chains. To which I pleaded, yeah, guilty, because it wasn't necessary to understand the theorems in all generality in cases when it's sort of obvious what's going to happen. In fact, the only time the mathematics becomes interesting is when what you expect to happen doesn't happen. Okay, so what I'm going to do is I'm going to assume that the limiting distribution exists just as we did before with birth and death processes, and take limits in this equation. So when I take limits, the k goes away and is simply replaced by pi star, with the subscript being the number of customers. So this is what I get. I assume that this limit exists, and so that those equations become this. The probability that an arbitrary departure, that's what the star means, leaves behind J in equilibrium is equal to the probability that the previous departure, the right-hand side is the previous departure, but they have the same distribution because I've gone to infinity. So that's the key. The probability that the previous departure left the system empty, in which case he will leave behind J if during the service time of the guy who just departed, exactly J new ones arrive according to a Poisson process. Plus the probability that the previous departure left behind I, where now I is between 1 and J plus 1, and during the service time that separates those departure points, the number of new arrivals according to a Poisson process would be exactly J minus I plus 1. So now I have to solve these equations. I solve these equations and I get the equilibrium distribution of the pi j stars. So So in other words, now I'm going to say let g of z equal the probability generating function of the equilibrium departure distribution. So what I do is I multiply through by z to the j, and I sum. Okay, so let me do that over here. So let me erase this. Any questions about this? Okay. I got to keep saying, though, that although this looks complicated, it turns out that when you actually use this, it's simple because everything collapses, everything works out neatly, which is characteristic of queuing theory. Okay, so what I'm going to do is I'm going to multiply through here by z to the j and add. So I have pi j star, and now I'm going to multiply by z to the j and sum as j runs from 0 to infinity. And by definition, that's g of z. Okay, so what does that equal? I multiply this term, and I'm going to get summation pj pi 0 star z to the j summed over all j. Then I'm going to multiply this by z to the j plus. So I have the second term is the summation as I runs from 1 to j plus 1 of p j minus I plus 1 pi I star. Then I multiply that, this sum right here, by z to the j, and I sum that over all j from 0 to infinity. This sum runs from 0 to infinity. So g of z is given by this. All right, so all I did here was write down the equations at departure points for the number of customers left behind by a departure, write down the transition probabilities, take limits, get this result here, and now I'm going to solve this set of equations, of which there's an infinite number of these simultaneous equations for the pi stars. I'm going to solve them by finding their generating function. So to find the generating function, I multiply through by z to the j and sum as j runs from 0 to infinity. So the left-hand side, by definition, is g of z, the generating function, and the right-hand side has some stuff which we now have to manipulate. Okay, so you can see what's going to happen here. The first term is simple. The pi 0 star is going to come outside the summation sign. And what I have left is, I forgot the j here, pj z to the j, summed as j runs from 0 to infinity. Okay, so what is that going to equal? Well, let me notice that if I calculate the sum of pj z to the j as j runs from 0 to infinity, that in fact is a generating function because it generates those probabilities right there. So let me call that, I'm going to give that a name, I'm going to call that h of z. Okay, so what is h of z? H of z is the generating function of these probabilities. This is the probability that during an interval of length t, that's a service time, exactly j customers arrive according to a Poisson process. So it'll turn out, you'll see shortly, that this generating function is easy to calculate. Okay, so what do we have here? We have pi 0 star, that's this guy, times this generating function h of z, plus this stuff right here. And I'm going to call that s. Okay? And now what I'm going to do is I'm going to do some manipulation of this and find out that this is going to give me an expression which is going to contain the generating function g of z, and it's going to contain the generating function for these guys, which is h. And then I'm going to relate this generating function to the Laplace-Dieltjes transform of the distribution function of the length of a service time, and we'll get an expression for G, and that will be the answer that I wrote down originally. So now I got to do some arithmetic on this thing called S. Yes? Okay. Okay, the strategy is that I'm going to manipulate these terms over here. When I manipulate this term, what I get is pi 0 star times this generating function. That generating function is the generating function of the number of customers that arrive according to a Poisson process during a service time. And in fact, that will turn out to be exactly equal to the Laplace-Dieltjes transform of the distribution function of the length of a service time evaluated at lambda minus lambda z. In fact, why don't I do that first? Okay, so I'm going to relate this to the Laplace-Dieltjes transform of the service time distribution function. Because remember, let me write down what the final answer was. Okay, let's go back here to 812. .812 says that the generating function that we're going to get, the answer when we get done with this part of the analysis, is given by z minus 1 eta of lambda minus lambda z divided by z minus eta of lambda minus lambda z times 1 minus rho. That's what we want to get to. That's equation 812. Now, what's the eta? Where eta, by definition, eta of S, was the Laplace-Dieltjes transform of the distribution function of service times. So if the service times are called H, then eta of S is given by this expression. This is the Laplace-Dieltjes transform. Okay, so what fits in here is the Laplace-Dieltjes transform of the distribution function of service times. It's easy to calculate, depending on what H is. I plug into here, and that gives me the Laplace-Dieltjes transform of the distribution function of service times evaluated at lambda minus lambda z. Okay, so let's relate that to the H of z. Okay, H of z is equal to, by definition, the generating function, the sum, pj z to the j, as j runs from 0 to infinity. Now, we did this last time because what I'm doing is I'm calculating the generating function of a number of customers that arrive according to a Poisson process during an interval whose distribution function I know. And if you remember, one of the things about Laplace-Dieltjes transforms and generating functions, the relationship was that the distribution of the number of Poisson arrivals during an interval is simply related to the Laplace-Dieltjes transform of the distribution function of the length of the interval. Okay, so if I were re-deriving that, what I would get is this. I'm going to take this thing and I'm going to multiply it by z to the j and sum it. So when I do that, I'm going to get the sum of lambda t to the j over j factorial e to the minus lambda t d h of t z to the j. And then I have integral. Okay, so I have the sum, as j runs from 0 to infinity, of pj, that's that, z to the j. And then what I did was I said, okay, now I'm going to interchange order of summation and integration. So the integral comes out here, and I erase it in there. And then I'm going to take the z to the j, and I'm going to combine it with the lambda t to the j. So the j comes in, z to the j comes in there. It's erased there. And then I sum this thing right here. And that, of course, is the Taylor series expansion of e to the lambda t z. And then I combine that exponential with that exponential, and I'm left with the integral from 0 to infinity of e to the minus, now let's see, it's going to be e to the minus lambda z t. E to the minus lambda t, that's that. E to the plus lambda zt, it's that. dh of t. But by definition, that's the Laplace-Dieltjes transform of this distribution function evaluated at that argument. That's the s. So if the Laplace-Dieltjes transform of h is eta, then this integral is eta evaluated at lambda minus lambda z. And that's where this term comes from right here. Okay, so we're going to manipulate this. We're going to get the answer in terms of h. Then I'm going to replace h by eta. And that gives me, okay,
You're going way too fast.
okay, I'll repeat it.
You're talking and making it sound easy, but we're trying to take notes and understand at the same time. It's just not.
Okay, of course it's in the book.
So, right, but notes.
Okay, let me say it again. All right.
You've got e to the negative lambda.
All right. First of all, let's go back a step. Where I'm sitting now is I have that this generating function is given by that plus that. I'm going to have to manipulate this to get something. First, let me look at this. The h of z, this is the generating function by definition. It's the generating function of the distribution of the number of customers that arrive according to a Poisson process during a service time. That's what that little pj was. Okay. Now, in fact, it's given by this. This is the probability that during a service time, exactly j arrivals occur according to a Poisson process. So I'm going to find the generating function of that. Now, previously I said, we proved, that the generating function of the number of customers that arrive during a random interval is simply related to the Laplace-Dieltjes transform of the distribution function of the length of that interval. It ought to be true that if I tell you how long the interval is, it tells you something about how many arrive. If I tell you how many arrive, it tells you how long the interval is. Okay, now, it turns out that that relation, though, is very simple. I'll derive it again. H of z, by definition, is this generating function, because that's what comes out of this analysis. Okay, so now I'm just going to replace the p that appears here with what its definition is. That's this. Then I'm going to interchange the summation and the integration. So I had written an integral here, and now the integral comes outside. I'm going to sum inside first. Okay. Then when I do that, I also had a z to the j. So I took the z to the j that was over here, and I included it with the lambda t to the j that was already there. So I wrote it as lambda t z to the j. Then I took this sum of something to the j over j factorial and said, but that's the power series expansion of e to the lambda tz. We did all this before. So that means that I'm now left with the integral of e to the plus lambda tz, e to the minus lambda t, dh of t. So I combine those exponentials by adding the exponent. That gives me e to the minus lambda z times t, dh of t. But now I recognize this as saying this is exactly, by definition, the Laplace-Dieltjes transform of this distribution function, except that what we called s is now lambda minus lambda z. So if eta is the Laplace-Dieltjes transform of h, then this generating function is eta with s replaced by lambda minus lambda z. So when I get done and I get this answer, it's going to have in it h of z. And I'm going to, because here it is, and I'm going to replace that h of z by eta of lambda minus lambda z. That's where the eta comes from. Okay, now that's the key here in terms of saying that this is for mg1, because now what this says is, assuming we've gotten this answer, which we haven't yet, but assuming we've gotten this answer, this generating function depends on eta, and eta depends on the distribution function of service times. So if I plugged in the distribution function of service times to be the exponential, then eta would be such that this thing would reduce to the generating function for the ordinary MM1Q, which we've already done. So it's a check. If the service times are something else, then in order to get this, I have to plug in whatever that something else is. In your case, in homework 6, it's going to be for service times that are constant, which is the next simplest case. All right, so what I have to do is I have to figure out what this is and then show that when I manipulate that and then solve for g of z, it gives me this. So it's going to reduce these complicated embedded Markov chain equations to the simple result, which gives me the generating function of the number left behind by a customer in equilibrium. It relates that to the Laplace-Dieltjes transform, the distribution function of the service times. So it's a function of the service time distributions. Okay, so what I got to do is I got to manipulate this. Of course, in the book, all it says is that this thing reduces to, and then writes down the answer because it's just a lot of algebra. But I'm going to do it and show you that that's the way it works out. The thing here you have to remember is you've got to not lose sight of the forest for the trees, because it looks like there's a lot of stuff going on. But once you go through it several times and you see what each piece is, then it sort of separates. Each one is like an individual thought. And it separates, and then you can see that what's happening is ultimately everything is just collapsing because that's the way it works. Because that's the way the Poisson exponential, all that kind of stuff works out. All right, so now what I want to do is I've defined S. Here's S. S, by definition, is the sum as j runs from 0 to infinity of the sum as I runs from 1 to j plus 1 of p j minus I plus 1 pi I star z to the j. Okay, so now let's write this out. So suppose j is equal to 0. When j is equal to 0, then I'm going to get the sum from 1 to 1. And this is going to be 0 minus 1 plus 1, or in other words, it's going to be p0. So when j is equal to 0, the inside sum has one term in it. That's p0. That's going to be I, which is 1, pi 1 star. J is 0, so it's going to be z to the 0. So when j is equal to 0, this stuff becomes p0 pi star 1 z to the 0. Okay, now let's take the next term, because j is going to run from 0 to infinity. When j is equal to 1, this is going to be the sum from 1 to 2. Okay, so I'm going to plug in now j equals 1, I equals 2, so it's going to be 1 minus 2 plus 1. So in fact, what I'm going to get here is the first term is going to be p1 pi 1 star z to the 1, and then the second term is going to be p0 pi 2 star z to the 1. Okay, so let's check that. I'm setting j equal to 1, the second term in this sum. So that's going to be the sum from I equals 1 to 1 plus 1, or sum from 1 to 2. So I'm going to plug in here, first of all, j is equal to 1, I is equal to 1, so there's going to be 1 minus 1, which is 0 plus 1, that's a p1. I is equal to 1, pi 1 star. J is equal to 1, z to the 1. Okay, the second term here, when I is equal to 2, then that means that this part is going to increase by 1, so the total value is going to decrease to 0. So instead of having P1, it's going to have P0. The I is now 2, so instead of having a subscript of 1, it's going to have a subscript of 2, and the j is still 1. Okay, then you do it for the case in which j is equal to 2. This is j equals 0, j equals 1, j equals 2. So this is going to be P2 pi 1 star z to the 2. This is going to be P1 pi 2 star z to the 2. And the third term is going to be P0 pi 3 star z to the 2. Okay, so now you can see what the pattern is. This is going to be P3 pi 1 star z cubed. This is going to be P2 pi 2 star z cubed. This is going to be P1 pi 3 star z cubed. And then there's going to be P0 pi 4 star z cubed. And the idea is now I'm going to sum this way, this way, this way, and so forth. Okay, so what do I have? Well, here I've got a pi 1 star, so I'll factor that out. Pi 1 star. That's this guy. Then I've got P0 z to the 0, P1 z to the 1, P2 z to the 2. That's the generating function of P. So that's h of z. Okay, well, how about over here? Well, I'll factor out the pi 2 star. What's left? P0 z to the 1, P1 z to the 2, and so forth. So let me write it like this. That's going to be the summation of Pj z to the j plus 1, right? But I'll write that z to the j plus 1 is I'll take a z outside and write that as z to the j. But when I do that, this thing that's right in here, that's still h of z. So here I had pi 1 h of z. Here I have pi 2 star zh of z. What am I going to have here? Well, I'm going to have pi 3 star, factor that out, p0 z squared, p1 z cubed. Well, that's the same thing as z squared times h of z. And of course, this one's going to give me pi 4 star z cubed h of z. So in other words, what I have at the moment is I have pi 1 star h of z plus pi 2 star z h of z plus pi 3 star z squared h of z, and so on. Okay, let me erase this stuff here so I have more room. And look at what I have here. Well, I could factor out the h of z. So I have h of z. What do I have left? I have in here pi 1 star plus pi 2 star z plus pi 3 star z squared, and so on. Well, this is beginning to look good now, because this is almost a generating function. So what I'll do is I will multiply and divide by z. So there I divide by z. Here I multiply by z. This gives me a z. That makes that a z squared. That makes that a z cubed, and so on. But what's in here? Well, except for the 0th term, this is the generating function of the pi stars, because it's pi star 1, z to the 1, pi star 2, z to the 2, pi star 3, z to the 3. So this thing right in here is the generating function that I'm looking for, except for the first term. Okay, so that's what S is. So I come over here and I replace this S by this. So S now has been replaced by h of z over z times g of z minus pi 0 star. Okay, we're getting somewhere, because now I can solve this equation for g of z in terms of h of z. There's the h of z. There's the g of z. So I solve it algebraically, and what I'm going to get, let's go through one more step. Okay, I'm out of time, so I think I'll start with this next time. Okay, so let me just go back over here. Where we are now is in the book. I'm at equation 828. Okay, so right now, this is equation 829. It gives me g of z in terms of an equation which has pi 0 star, h of z, and itself. So I'm going to solve this algebraically for g of z, and then it's going to be in terms of, the answer is going to be in terms of the h of z and the pi 0 star. As we'll argue, the pi 0 star, that's the probability that a customer leaves the system empty, which is the same thing as the probability a customer finds the system empty, which is 1 minus rho. And the h of z is the generating function of the number of arrivals during a service time. That's the Laplace-Diels transform of the service time evaluated at lambda minus lambda z. So the 829 leads directly to the 812, which is our final answer. So I'll outline this again next time, go through that last step, and then we're going to go from the generating function to all of the things we want. Okay, then the next step will be to look at this for the case where the number of waiting positions is finite, which is your homework 6.